Look at this structure. It might seem terrifying and utterly lifeless, but believe it or not, this is our home, Earth, at the dawn of its existence, some 4.6 billion years ago. How our planet, and the moon for that matter, formed still remains shrouded in mystery. Today, we'll explore scientific theories that shed light on these grand cosmic events. You'll discover how radically different planets emerge from the same swirling clouds of dust and gas. Learn which celestial body may have slammed into Earth long ago. Find out where our planet's vast supply of water came from, and learn how old Earth's oldest known organism might be. We've prepared the story of our world, tracing its journey from a tiny clump of dust and gas only a few miles wide, all the way to the spark of life. When the sun ignited, gases and particles nearby began colliding, gradually forming small building blocks known as planetesimals. As gravitational forces intensified, these growing seeds pulled in more material and expanded until they became true planets. Our solar system's gas giants, Jupiter, Saturn, Uranus, and Neptune, were born long before the four familiar terrestrial planets, Mercury, Venus, Earth, and Mars. But how exactly did our home planet come to be? Earth's story began about 4.6 billion years ago, amidst a disc-shaped cloud of dust and gas encircling the newborn sun. We know this because of the fossil record and through dating some of the oldest materials found on Earth, zircon crystals over 4.3 billion years old. Yet despite this knowledge, the precise mechanism of Earth's formation is still not fully understood. Two leading theories try to explain how planets form. 1. The core accretion model. About 4.6 billion years ago, a swirling solar nebula formed our sun, leaving behind material of different sizes, orbiting at slightly varying speeds. Over time, these particles collided and stuck together, guided by gravity, forming larger and larger structures, ranging from a few miles to hundreds of miles across. As the solar wind swept away lighter elements like hydrogen and helium, only rocky materials remained close to the sun, coalescing into terrestrial planets like Earth. Farther out, in regions where solar winds had less impact, lighter elements persisted, allowing massive gas giants to form. NASA considers core accretion the most widely accepted model, suggesting that small rocky worlds like Earth are more common in the universe than gas giants. However, while this model explains how terrestrial planets form, it struggles to account for the quick assembly of giant planets. That's because researchers believe the Sun's gaseous disk didn't last more than 4 or 5 million years. Apparently not enough time for gas giants to form under the core accretion model. 2. The disk instability model. This newer theory suggests that massive clumps of dust and gas rapidly coalesced early in the solar system's existence, forming giant planets much faster than core accretion allows, potentially within just 1,000 years. This speed would enable these worlds to capture lighter gases before they vanished. Recent studies propose that proto-Earth emerged in about 5 million years. If we compress the solar system's entire 4.6 billion year history into a single day, Earth's assembly would have taken a mere 1.5 minutes. If this is correct, water, essential to life, might be a natural byproduct of planetary formation. Such a scenario means we might be more likely to discover life's building blocks beyond our own solar system. The moon's mysterious origin. What about our companion, the moon? Astronomers have put forth many hypotheses. One wild idea, called the fission theory, posits that Earth spun so fast in its molten youth it flung off a chunk that became the moon. Another, the capture theory, suggests the moon formed elsewhere and was snagged by Earth's gravity. A co-formation theory holds that Earth and Moon formed side by side from the same dust and gas, but the prevailing and most mind-blowing theory is the giant impact hypothesis. A Mars-sized planet named Theia may have collided with Earth, ejecting molten debris that coalesced into the Moon. This explains why Earth and the Moon share similar isotopic signatures but have different core compositions. Heat, differentiation, and cooling. In its infancy, Earth was a molten world bombarded by asteroids and heated by gravitational compression and radioactive decay. As it cooled, minerals crystallized and materials separated by density, forming Earth's crust, mantle, and core. But how did water appear on a scorching hot rock adrift in space? Today, oceans cover more than 70% of Earth's surface. Yet no other known terrestrial planet in our solar system holds as much liquid water. Scientists have several theories. Maybe comets or icy asteroids delivered water. Perhaps hydrogen-rich minerals within Earth melted and released water as steam, which eventually fell as rain. Volcanic outgassing might have played a crucial role, releasing water vapor trapped beneath Earth's crust. Over billions of years, countless impacts and geological processes provided the watery environment crucial for life to begin. The spark of life probably emerged around 3.8 billion years ago. Tiny hematite tubes from 4.28 billion-year-old rocks suggest life's earliest roots stretch astonishingly far back in time. Was life sparked by chemical reactions in Earth's atmosphere and oceans, fed by hydrothermal vents on the ocean floor, or even carried here by extraterrestrial visitors like comets and meteorites? We may never know for sure. The early atmosphere was nothing like today's. It lacked oxygen and was rich in methane, carbon dioxide, sulfur, and nitrogen compounds, a composition found on some bodies in our solar system even now. Laboratory experiments simulating lightning in such a primordial atmosphere produced amino acids, essential for proteins. Perhaps early life didn't need sunlight at all, and used Earth's inner heat to power its existence. Or life's origins might lie in space, giving hope that life could be common throughout the cosmos. Evolving complexity. Over billions of years, tiny microbes and single-celled organisms evolved, feeding on methane. Around 3.6 billion years ago, viruses likely emerged. Photosynthetic cyanobacteria later transformed Earth by releasing oxygen as a waste product, poisoning many early life forms but paving the way for more complex organisms to flourish. Geologic eras came and went. Land masses fused into supercontinents and broke apart. The Earth froze and thawed multiple times, challenging life but never eradicating it completely. Over time, worms, fungi, arthropods, mollusks, and eventually vertebrates emerged. Plants took root on land, and insects proliferated, adapting and surviving through changes in climate and oxygen levels. Amphibians, reptiles, and other creatures rose and fell as mass extinctions periodically reshaped life's tapestry. The rise of dinosaurs and beyond. The dominance of mammal-like reptiles gave way to the age of dinosaurs. These magnificent creatures evolved into forms large and small, filling every niche on land and at sea. Feathers, possibly for insulation, appeared long before birds took flight. Giant herbivores, armored plant-eaters, swift predators, and colossal sauropods all had their time under the sun. Yet another catastrophic event. An asteroid impact 65 million years ago brought the dinosaur era to a close, clearing the stage for mammals and, ultimately, humans. The threat from space scientists have learned a great deal about that fateful asteroid impact in what is now the Gulf of Mexico. The colossal blast triggered wildfires, tsunamis, and nuclear winter-like conditions. Yet life endured, and from those ashes emerged the world we know today. NASA's ongoing research ensures we remain vigilant, tracking potentially hazardous asteroids and experimenting with ways to avert catastrophe should one head our way. Conclusion. Our planet's story is one of unimaginable violence and delicate balance, of fiery origins and miraculous resilience. Over billions of years, Earth transformed from a lifeless molten rock to a blue world teeming with organisms.